Today we're going to look at representing functions as power series. So in a recent video we learned about power series, and remember that a power series had this form starting from 0 to infinity. We had some sort of coefficient and then x to some power. And so if we were to list that out, we essentially would have our first coefficient x to the 0, which would just be 1, plus our our 0th coefficient, Then our first coefficient x plus our second coefficient x squared, and then that continues forever and ever. So essentially a power series is an infinite polynomial. And then we could also have it centered at a different spot. So right now the one that I currently have written is centered at 0, but we could have it centered at a instead, and then we just would have x minus a to the n, and then this would be c sub 0, c sub 1, x minus a, c sub 2, x minus a squared, etc. Okay, so this centered at a, centered at 0. Most often we will have the power series centered at 0 just because it's just kind of easier that way. So you might recall from the previous power series video that we looked at that we saw this function, g of x, equals the sum from 0 to infinity of x to the n. So if I were to write this out, I would have 1 plus x squared plus x cubed plus x to the 4th, ... So this function, this is essentially geometric, isn't it? So, if you think about x as being like r, so we know that the geometric series converges whenever the absolute value of r is less than 1. And so we saw that this power series has a domain of -1 to 1 because we checked the endpoints as well, and we can see that the series -1 to the n would diverge. It would just alternate between 1 minus 1 plus 1 minus 1 plus 1 minus 1. So the partial sums would alternate between 0 and 1 and would never actually approach anything in particular. And so that series diverges. And then the more obvious endpoint, 1 to the n, which would just be 1, would be the series 1. And imagine adding infinitely many 1s, right? You would end up getting infinity. So the endpoints didn't check out, and so that's why we have this open interval of -1 to 1. And recall that this domain is also called the interval of convergence. And that means that the radius of convergence in this particular case is 1. Just a little reminder from what we learned last time. So due to its properties of being a geometric series, right, I want us to think about, we know that it converges, right, for this specific interval, -1 to 1, not including the endpoints. So the question I would have for you then is, what does it converge to, right? Because we learned that geometric series, when we learned about geometric series, we had the index starting at 1, and we had a r to the n minus 1, but you can easily switch this so that the index starts at 0, and is then ar to the n. So both of these are the same geometric series. Notice they both start out with an exponent of 0. So depending on the approach, you can see it written either way, but doesn't really matter. This series, this geometric series, converges to a over 1 minus r, again, when the absolute value of r is less than 1, which we have already kind of established that with our interval of convergence. So with that in mind, that means that this power series converges to, well, notice the a value here, which I circled, that's not a 0. This a value is just 1 over 1 minus, and then the r value in this particular case, since it's a power series, is x. So it would converge to 1 over 1 minus x. So that means that the function 1 over 1 minus x can be represented with a power series, in this case, this particular power series, only on a certain interval though. So let's do a little exploration really quick. I do have an example and then another technology exploration, but I think I would actually like us to take a look at the technology exploration up here real quick. So let's go ahead and go into Desmos, and what we're going to look at in Desmos is comparing the function 1 over 1 minus x to its power series. which is this power series. So in Desmos, we're going to essentially look at the nth partial sum. So remember, we've done this before in Desmos, where we look at the nth partial sum and then kind of get an idea of whether the series converges or diverges. But in this case, or in previous cases, the nth partial sums were numbers, weren't they? And we kind of looked at what those numbers appeared to be approaching. In this case, the nth partial sums are going to be different functions of varying degrees. So for example, the 0th partial sum of this power series is going to be just x to the 0, which is 1. The first partial sum is going to be the 0th, right, plus the next term, which would be x to the 1, which is x. The second partial sum would be 1 plus x squared. The third, 1 plus x squared plus x cubed. So notice that what we have is the partial sums of the power series are polynomials of varying degree. In this case, the degree of the polynomial matches the degree of the partial sum. That won't always be the case. In this case, it's just because it's n here. Sometimes we'll see it might be a 2n or a 4n or something like that. So we're going to be graphing this function and then graphing increasing degrees of the partial sum to see how that relates to the power series and to see how that relates to the interval of convergence. Here we go. All right, so in Desmos, let's go ahead and start by graphing the function itself, which was 1 over 1 minus x. Okay, so notice that the domain of 1 over 1 minus x is all numbers except for x equals 1. We have a vertical asymptote at x equals 1. But we're going to see a different domain in the power series, right? With the power series, we saw that the domain was -1 to 1 because of it being geometric. Okay, so since we're going to graph the power series, we're going to go ahead and do sum, S-U-M. And again, we want to do the nth partial sum. We're going to do a slider in this case. So we want the upper bound of our sum to be n, which means that we need to change the index to be something else. I tend to choose I. I equals 0 to n. And then it was x to the, I'm going to use I, right, instead of n. Now it's asking me, do you want a slider for n? I'm going to say yes. And I'm going to change the kind of the interval of n. So maybe we can go from, let's start with 0 to 10. I think that sounds good, with a step of 1. Okay, and I'm going to start with n equals 0. So again, notice the partial sums here. Like the 0th partial sum is just a constant, 1. The first partial sum is 1 plus x, which would be linear. The second is 1 plus x squared, which would be quadratic, right? And then cubic and et cetera from there. So notice that as we increase the n value here, so notice right now the 0th partial sum is just 1, that constant, and then now it's linear. Notice that it's nicely tangent at the center, 0. And then at 2, now I have a quadratic. So notice it's fitting the curve a little bit better now. And then we're going to keep going. Now it's a cubic. Now it's to the 4th, 5th. So notice what's happening is that it just kind of keeps, as we increase the degree, it's becoming more and more accurate to the curve. I'm going to go ahead and make n 50 just so we can kind of keep going with this idea. And you might be wondering, like, why is this part kind of flipping back and forth, up and down? And that's because it's changing from being an even, well, I guess it's changing from being an even degree polynomial versus an odd degree polynomial. And so it's changing from a cubic shape to more of a quadratic shape as you kind of switch back and forth. But notice it's just getting better and better. But a big thing to point out here is that although it is improving, notice that it never does anything very well over here to the left of -1, right? And same thing to the right of +1. So we can kind of see that it seems like the interval of convergence would be -1 to 1. And you might argue, well, but the curve keeps going past -1 over here. And yes, but notice they're getting farther apart from each other. Like it's not a very good approximation to the left of -1, whereas around -1, it's looking pretty good. And then between -1 and 1, essentially. Okay, so not only are we seeing that this appears to be a good power series representation for 1 over 1 minus x, we're also seeing that it's only a good power series representation for x between -1 and 1, as we would expect. So let's keep going and see if we can come up with even more functions that we can represent with a power series. And just as a little reminder, anytime that we represent a function as a power series, or as the sum of a power series, we need to make sure that we include the interval of convergence and state that this is a power series representation for this function whenever x is blank, right, on some particular interval. So moving forward, let's take a look at example 1. And really, all of these next examples are going to be, how do I want to say this? They're going to be finding power series representations for functions that are similar to this one here. Sorry, I'm trying to get orange. Come on, orange, be my friend. There we go. So we're going to be essentially manipulating this power series representation, 1 over 1 minus x equals the sum from 0 to infinity of x to the n. We're going to be manipulating this power series to create new power series. And some of those manipulations are going to be substitutions, like replacing x with something different, or we could multiply through by either a constant, or we could multiply through by x to a power to create something else. We could integrate, we can differentiate. There's lots of things cool things that we can do to tweak this power series to create new power series representations for different functions. Okay, so that's what we're going to be looking at doing. So here in example 1, we are going to express 1 over 1 plus x squared as the sum of a power series and then find its interval of convergence. So 1 over 1 plus x squared. Let's kind of think about what we would do to 1 over 1 minus x in order to make this into 1 over 1 plus x squared. Notice that they're kind of similar. They have 1 over 1 then something. In this case, this is 1 over 1 minus x. And what I'm looking to obtain is 1 over 1 plus x squared. So we can kind of think about what we would need to change in this part in order to make this a plus x squared instead of a minus x. So if we were to replace x with something, we could make this into a 1 over 1 plus x squared. So I'm going to actually erase the minus x part here and just circle the x part. If we replace x with negative x squared, I would then get 1 over 1 minus negative x squared, which notice is 1 over 1 plus x squared, which is the thing that we are looking for here. So this is going to be all about manipulating that power series, 1 over 1 minus x, again, to create new power series representations for other functions. So here we go. Let's go ahead and do that. Now I know that if I look at 1 over 1 minus x, this power series is x to the n. Now I'm going to do two different things. I'm going to be representing these power series in their more like expanded form with the pluses and the dot dot dots, and then in the more condensed form with the sigma notation, just so we can play around with both of them and see how these manipulations affect them either way. So again, this is 1 plus x squared plus x cubed. Actually, you know what? I'm going to rearrange, sorry to move this on you. I'm going to rearrange this because I actually kind of like to have the expanded form written first and then the condensed form written last. Cubed, dot, dot, dot. And then, so then here's the closed form, x to the n. Okay, so now when I do 1 over 1 minus, I'm going to, again, replace the x with a negative x squared. And doing that will create the 1 over 1 plus x squared that I'm looking for. So now when I do that replacement, when I replace this x here, I just need to do that in all the other situations as well. We're going to replace all of these x's with a negative x squared. So I'd have 1 plus negative x squared plus negative x squared squared, right? Squared plus negative x squared cubed. And now I feel pretty comfortable doing the dot, dot, dot. Now we're going to also do that in the sigma notation form. Negative x squared to the n. Okay, so again, we've taken this power series representation for 1 over 1 minus x and manipulated it to now get one for 1 over 1 plus x squared. So here we go. This is now 1 over 1 plus x squared. And I now have, let's just simplify this a little bit. This would be 1 minus x squared. And so we're going to just kind of go through and simplify these. Negative x squared squared, notice I would square the negative. Squaring a negative gives me a positive. And then x squared squared would be an x to the fourth. Now, cubing a negative is a negative, so this is going to be minus. Notice what's going to happen here is kind of cool. We're going to now get an alternating power series. And so x squared cubed would be x to the sixth. So just as an algebraic reminder, we multiply the exponents together, right? When we have x to the a to the b, this is x to the ab. Multiply those exponents together. So the next one would be plus x to the eighth, but I'm just going to go ahead and go with my plus dot dot dot. And notice what we have over here now in the closed sigma notation form, we would have negative, you could think of it this way, negative to the n, you can think of that as negative 1 to the n, right? That's going to be the alternating component, alternating factor. And then it would be x squared to the n. We again multiply those exponents and get 2n, which makes sense because notice that all of these powers are even, and 2n is how we create an even number. Okay, so that means that this is the power series representation for 1 over 1 plus x squared. Now the second question is find its interval of convergence. So the interval of convergence would be, again, this is not going to be true for all x. It's only going to be true for a specific range of x values. In that particular range of x values, let's write it over here, interval of convergence. Now we know that this interval of convergence was that x, absolute value of x had to be less than 1. So just like over here where I replaced all of the x's with a negative x squared, I can do that here also. I'm going to replace that x with a negative x squared, and what I end up getting is that the interval of convergence is that the absolute value of negative x squared has to be less than 1. But this would be the same thing as saying that x squared, right, because the negative sign, I'm taking the absolute value. Same thing as saying that x squared has to be less than 1, which is still saying that absolute value of x has to be less than 1. Because if you imagine, if you think about squaring a number and having it be less than 1, it could have been a negative number, but it would have had to be bigger than negative 1, and it would have had to be smaller than positive 1. And so another way you can write that is absolute value x is less than 1. You can also think of it as square rooting both sides of the inequality sign. But when you square root x squared, you get absolute value x out when you do that. So this is our interval of convergence, which notice means that it hasn't changed, right? It's still negative 1 to 1. We would still potentially want to check the endpoints. We could go ahead and do that. We can just kind of do that mentally, just make sure. So I'm going to start by saying negative 1 to 1. Like so, and then but let's check the endpoints real quick just to make sure. So again, imagine plugging in 1 for x here. I'd have 1 to the 2n, and so what series I would get would be just an alternating series, negative 1 to the n. That would end up diverging, because again, the partial sums would be positive 1, negative 1, or sorry, positive 1, 0, positive 1, 0, positive 1, 0, because it'd be 1 minus 1 plus 1 minus 1. If x was negative 1, now, since this is always going to be an even power, negative 1 to the 2n is always going to be positive 1, and so we get the same series, whether x is positive 1 or negative 1. It would be the series negative 1 to the n, which is also going to diverge. So we have the same interval of convergence, negative 1 to 1. So let's go into Desmos real quick, and we'll kind of see another representation of now this new power series, and see how that interval of convergence comes into play again. So now I've got 1 over 1 plus x squared. This is a great way to check your answer, by the way. So notice that, and I'm going to kind of zoom in a little bit here. Notice that what I have is 1 over 1 plus x squared. I changed that function. I have not changed the power series representation yet. Notice that this current purple power series representation is not good for 1 over 1 plus x squared. And that's because it's the power series representation for 1 over 1 minus x, right? So let's tweak this. And now this is going to be, we're going to change this to the power series representation that we just came up with. So it was -1 to the n, but I'm using I for the index, and then it was x to the 2n, so 2i. Okay. Did I get all of that there? Let me double check. Okay, that looks good. And now notice what's happened is kind of our curve has adjusted. I'm going to kind of scale it back for a second, back down to maybe like, we'll just start at 0. I just want to show you kind of, you know, seeing it fit the curve as we increase the partial sum. So 0, so notice that's just a straight line, not very exciting. And then we have a, notice that when n equals 1, we now have a quadratic. And that's because when n equals 1, we have a squared term, right? This is the first partial sum. So the 0th partial sum is 1, then the first partial sum is 1 minus x squared. The second partial sum is this, and then the third partial sum. So you can kind of see we're getting pretty good accuracy here, even with small n values. Okay, kind of see it flipping up and down based on the even versus odd. But it appears to be getting, right, it gets better. It's fitting the curve even better as we go. But it never seems to improve from -1 to 1, does it? So it's kind of interesting. It almost looks like they are the same curve, doesn't it? And you can kind of even, you know, zoom out a little bit. It almost looks like they're identical on this interval. Not necessarily -1 to 1, but kind of close to that. Maybe like from right here to about here. But here's the really interesting thing. These two curves are only equal to each other at this center point, 0, 1. That's where they're equal to each other. Everywhere else, they're not equal, but they are very, very close approximations to one another. And we'll start to look at some applications of these power series, some of which are we can use the power series to approximate the function at a specific point. And it's other ones we can look at finding definite integrals, so maybe some function that doesn't have an antiderivative, we can use power series to help out with that. We're going to do an example like that in a little bit. I'm getting ahead of myself. I just think these are so cool. Okay, so moving forward, let's take a look at some more examples here. Let's find a power series representation for 1 over 2 minus x. And then again, we're going to find the interval of convergence. Okay, so the way that we're going to do this one, and again, I'm going to point out that this is kind of always going to be our starting point. This is something you're going to want to remember. Now, it shouldn't be too hard to remember, because if you just remember what a geometric series converges to, this comes directly from that, doesn't it? So we're going to make that our starting point, and we're going to need to think, well, how do we need to tweak this in order to get this, right? So I'm going to think of 1 over 1 minus x. How do we kind of get that into a 1 over 2 minus x? Now, in the previous example, we replaced x with something, right? We replaced it with a -x squared. In this case, I can't just, you kind of see the difference here is that this 1 is now a 2. I can't replace 1 with 2, right? 1 is not a variable. 1 is 1. I can't really do anything to change that. All I can really do is change what x is to somehow get a 2 minus x instead of a 1 minus x. And here's how we're going to do that. This might not feel 100% intuitive, but bear with me on this one. So 1 over 2 minus x. If I essentially want to get this to become a 1 so that it's more like this, what I can do is I can factor a 2 out of that denominator. If I pull a 2 out, what I'm left with is the 1 that I needed, right? Because we were kind of trying to get it to look more like this. Minus, not minus x, right? If I factor a 2 out, I factored it out of the 2, I also factored it out of the x. And so this would now be an x over 2, right? So this can be written as 1 over 2. Well, actually, I'm going to write this as 1/2 times 1 over 1 minus x over 2. Now, I'm going to point out, if you distribute this 2 through, notice that what you end up getting is 1 over 2 minus x, right? It's equivalent to 1 over 2 minus x, but notice it is now more similar to this form than it was before. This 1/2 is just a scalar multiple, which I can multiply both sides of this in order to get a 1/2 involved, and then I can replace x with something, in this case with x over 2. So we're going to have to do two things to the power series in order to get it to look like this. Okay, so we're going to start with, again, what we know, which is that 1 over 1 minus x is 1 plus x squared plus x cubed, dot, dot, dot. And the closed form of that is the sum from 0 to infinity of x to the n. So now we're going to do 1/2 times 1 over, maybe we should just do one step at a time actually here, instead of doing two things at once. Well, let me think about this. I think in this particular case we could probably do it all at the same time, and it doesn't matter the order in which we do these. Like, I can multiply through by 1/2 first, and then replace the x with x over 2, or I could do it in the opposite order. Sometimes it's going to matter the order in which you do something, and we'll see some examples in just a second like that. So I think hopefully we're feeling okay if I were to do this in one single step. So we're going to go ahead and replace the x over 2, or sorry, replace the x with x over 2, and we are also going to multiply through by a 1/2. I think I'll go ahead and write it this way. 1/2, so I'm multiplying both sides of this equation with 1/2, and then I'm going to replace all of the x's with x over 2. 1 plus x over 2 plus x over 2 squared plus x over 2 cubed. Sorry, my pen color doesn't always switch when I tap on it. Plus dot, dot, dot. And then we're going to also replace that here. Now notice that we multiplied by 1/2 on the outside, so I'm going to go ahead and put that on the outside of the sigma notation here, but we might be able to bring it in a little bit. And then again replacing x with x over 2 to the n. Okay? Now let's clean this up a little bit. So the left side I'm going to actually write as the thing I was originally wanting to find, which is 1 over 2 minus x, right, which again is equivalent to this. I'm just kind of, this step here tells me like what I need to do to 1 over 1 minus x in order to get the thing I'm looking for, which is 1 over 2 minus x. Okay, so let's go ahead and distribute the 1/2 through. So this would be 1/2 plus, now x over 4, plus, this would give me x squared over 4, but times the 1/2 again would give me x squared over 8, plus x cubed over 2 cubed, which is 8, but times another 2 would give me 16. And we'll go ahead and proceed with the dot, dot, dots now. Now the reason why I write this in both forms, right, with the closed form and the open form, is, I mean, technically you could just do this and then try to come up with a pattern, right, to figure out what the summation is. But you can also see that come in with just, you know, simplifying it in this form too. So I can bring the 1/2 in. It'll be 1/2 times x to the n divided by 2 to the n, which notice would give me x to the n over 2 to the n plus 1. That can be written that way. Okay, so this then is the power series representation. I think maybe I'll go ahead and write this down here. This is the power series representation for 1 over 2 minus x. So there we go. Now we want to find the interval of convergence. Okay, so looking at the previous interval of convergence for this one, it was, again, absolute value x has to be less than 1. Notice the two things that we did when we manipulated 1 over 1 minus x to get 1 over 2 minus x. We, again, did two things. One of the things that we did is we multiplied through by 1/2. Now, if you imagine multiplying a power series by a constant, that won't affect the interval of convergence at all, right? It's just the only thing it will affect is the overall sum. Now the overall sum will be half of what it previous was, but it won't affect which x values the power series converges for, right? So that's not going to change anything. So don't have to worry about that multiplication by 1/2 affecting the interval of convergence. What is going to affect the interval of convergence is replacing x with something else, which is what we did here, right? We replaced x with x over 2. So just like before, in this one, we replace x'd with a negative x squared. Now we're going to go ahead and say, well, what we did is we replaced x with x over 2, and we still now need the absolute value of x, in this case x over 2, to be less than 1. So we now have this absolute value inequality to solve, which we should be feeling pretty good with after doing power series and finding all those intervals and radii of convergence. So what we can do is look at the absolute value of x over 2, right, because the absolute value of 2 would be 2, is less than 1, and so we end up getting the absolute value of x is less than 2. So that's interesting. Notice what we've done here is we've essentially doubled our interval, or, well, you could say doubled the length of our interval of convergence, or you could say we've doubled the radius of convergence to now be a length of, the radius of convergence is now 2, or the length of the total interval is now 4. And so yeah, so this is our interval of convergence. Absolute value of x has to be less than 2. We should check the endpoints just to kind of see if we can potentially include those or not. Most of the time we can't, but you know, we should check them just in case. One thing I'm noticing is we definitely can't include x equals 2, because if you look at the left side of this power series, the power series representation for 1 over 2 minus x, if x was equal to 2, I would end up having 1 divided by 0. So we definitely can't let x be 2, but I'll just double check that over here with the power series too to see another way of thinking about it. If x is 2, what I would end up having is the series 2 to the n over 2 to the n plus 1, which would simplify to 1/2, wouldn't it? Because you've got just an extra 2 in the denominator each time. Imagine summing infinitely many 1/2s. That definitely diverges. If x was negative 2, what I'd end up having is, think of this as a negative 1 to the n, an alternating piece, times 2 to the n, and this would then be the alternating series. Well, it'd just be a bunch of alternating 1/2s. 1/2 minus 1/2 plus 1/2 minus 1/2 plus 1/2 minus 1/2. That is also going to diverge. So we can see that we would not include the endpoints. Our interval of convergence would be negative 2 to 2. And as always, I kind of like to check my answer in Desmos. So let's just tweak what we currently have in there to now be the function, oopsie, 1 over 2 minus x. And then this became, I might have to go back to remind myself, it wasn't a 2. Sorry, thanks for being patient with me. It would be x to the I divided by 2 to the I plus 1. Looks like we're going to have to put that exponent in parentheses so that we end up with the plus 1 in there. Okay, there we go. I'm going to again kind of bring it down a little bit and zoom out here a little. Okay, so now we'll increase the n. It looks like a good fit. And notice that it does extend beyond negative 1 and 1, and it appears to be going from negative 2 to 2. So you can kind of imagine how this would affect other things, like instead of 1 over 2 minus x, if I had 1 over 3 minus x, how would that be different? Well, essentially, it would just be, now it would be having a 3 here instead. And then notice that that extends the radius of convergence. Again, now the radius of convergence would be triple what it previously was. 1 over 4 minus x would be having a 4 here. And again, notice that now our interval of convergence is from negative 4 to 4. Okay, so you can kind of use that idea as you work through your homework. But it is, you should still be showing your work every time, though, if there's an example like this, like a 1 over 2 minus x. Okay, I have one for you to try now. So go ahead and pause the video. And I'd like you to try to find a power series representation for x divided by 1 minus x cubed. Now, before you do it, I'm going to give you just a little bit of a hint. It's going to use kind of two, it's going to use the kind of situation that we did in example 1 and in example 2. So you're going to need to replace x with something, and then you also might need to multiply through by something in order to create this x here in the numerator. So go ahead and pause it and give it a try on your own. Okay, welcome back. Hopefully that went pretty well for you. Okay, so we are, as always, going to start with 1 over 1 minus x, and in this case we're now trying to get x over 1 minus x cubed. We're going to kind of manipulate this 1 over 1 minus x in order to get that. So in order to do that, what we're going to do is we're going to think about multiplying through by x times 1 over 1 minus, and then we're going to replace x with x cubed. Right? So this makes this happen, and then writing it this way we can kind of see what needs to be done. So we need to replace x with x cubed, and then we need to multiply both sides by x. Okay? All right, let's try to do that. So I'm going to again write this thing that I'm going to plan to do. Well, actually, I'm going to start with the thing that we know. 1 over 1 minus x is equal to 1 plus x squared. You might not have to do as many steps as I'm doing, and that's okay. I generally like to show as many steps are needed. And so we're going to try to now create x times 1 over 1 minus x cubed. You can do this in one step, or you could do this in 2 steps. Let's go ahead and, I'm going to go ahead and do it in 1 step, hopefully. I know I just said I like to show as many steps as possible. How hypocritical of me. So we're going to multiply both sides by x. Okay, so I'm essentially multiplying this by x, and I'm going to do it here as well. And then what we're going to have is, on the inside, we're going to now replace all the x's with x cubes. Sorry, my keyboard keeps kind of thinking it's getting detached. That's why you're seeing that pop up sometimes. Maybe I will actually detach it, and then we won't keep doing that. Okay, that's the last one, I promise. Okay, and then x cubed squared plus x cubed dot dot dot. Now, I'm not going to do, well, let me think about this. So since the sum is in terms of n, I can write x on the outside of the summation. It does feel a little bit strange to me to write that, but I'm going to do that just because that's kind of how I had it over here as well. Okay, and then it'd be, instead of x to the n, it's going to be x cubed to the n. Okay, so again, we did 2 steps there. We multiplied all the sides by x, and then we replaced x with x cubed. And that is what creates this, which is x over 1 minus x cubed, the thing I was interested in. And now we're going to go ahead and simplify this. You could do this in 2 steps or 1 step. I'm going to think about distributing the x through, in addition to computing some of these exponents to exponents. Here we go. X plus, right, that's this one here, and then it'd be plus x to the 4th, plus, now this is going to create an x to the 6th, but times x is going to give me an x to the 7th, plus, this would be x to the 9th, plus another 1 would be x to the 10th, plus dot dot dot. And now this is going to be, this would give me x to the 3n times another x is going to add 1 more to it. So this would be x to the 3n plus 1. Now you can always go back and kind of make sure that this fits the pattern that you're seeing here. We see a 3n plus 1 exponent. So notice the 0th n is x to the 0 plus 1, which is x to the 1. Check. And then if I were to do n equals 1, I would have 4. N equals 2 would give me 7. N equals 3 would give me 10. So yep, that's looking good to me. Okay, so this is the power series representation for x divided by 1 minus x cubed. Let's go ahead and find the interval of convergence. Now, multiplying through by x, similar to multiplying through by 1/2, is also not going to change the interval of convergence because it's just multiplying through by essentially like a constant. Remember, x is a variable, but it's a variable that represents, a number within the function. So we don't have to worry about multiplying through by x being anything that's going to change the interval of convergence, but anytime you replace x with something, that can change it. So the interval of convergence normally is the absolute value of x is less than 1. But now we replaced that x with an x cubed. Now, if the absolute value of x cubed is less than 1, then that's the same thing as the absolute value of x being less than 1. You could think of cube rooting both sides if you wanted to. Cube root of 1 is 1. So essentially, if you cube a number and you get a number that's less than 1, that number would have had to have been less than 1 to begin with, right? I can't cube 2 and get a number that's less than 1. Hopefully that makes sense. So we have the same interval of convergence of -1 to 1. We can kind of mentally check the endpoints. If I let x be -1, notice I would end up having it would be alternating, and so it would just be alternating between -1s and positive 1s. So that's not going to converge. And then if I did +1, it would be 1, it would just be the sum of 1s. Infinitely many 1s would diverge. So this is our interval of convergence. Okay, so we've looked at quite a few examples now of manipulating that 1/1 minus x to get something new, right? A power series representation for a new function. And we are now going to look at how we can do the same thing, but now with using the idea of differentiation or integration. So the idea is if you have a power function, now this one, notice, is centered at A, and if we have a radius of convergence that's not just converging at its center point, it's converging for some positive value r. There's more than one x value that this power series converges for, is essentially what that is saying. Then this function is differentiable on that interval, right, and is therefore continuous on that interval. And so that means we can take the derivative, right? We can essentially take the derivative of both sides and now get a power series representation for f prime of x and create a new power series, right? A power series representation for a new function, whatever the derivative of f prime of x, whatever the derivative of f of x is. Similarly, we can integrate as well and find a new function and a power series representation for that particular function. So notice when we go through that differentiation process, right, the derivative of a constant is 0, and then the derivative of x minus a would be 1, so notice that that just gives me that constant c1, and then we would have the derivative of this piece, c2 x minus a squared. So notice with the chain rule, I'd always be multiplying by the derivative of x minus a, which is going to be 1. So this 2 would come down. Notice I have 2c2 x minus a to the first power, right? So we're just seeing the power rule getting used each time, which is pretty great because I would think that you would agree that the power rule is pretty easy to use. It's very easy to take the derivative of a polynomial, and so that's why it's great. We can represent derivatives or integrals as power series relatively easily because differentiating or integrating polynomials is pretty straightforward. Now remember that when we integrate, we do the power rule for integrals. So the antiderivative of a constant is going to be that constant times, in this case, x minus a, because that's the center. Then the antiderivative of this would be the constant. And then remember what we do is this is currently an exponent of 1. We add 1 to the exponent and then divide by that result, right? So notice that's what we get here. And similarly, we add 1 to the exponent and then divide by that result. So we're just integrating each piece basically as we go through. And just recall that when you integrate something, you always have this arbitrary constant as well. So notice we have this plus c kind of on the outside. We tend to write it on the left of the sigma notation. If we were to write it on the right of the sigma notation, it wouldn't be quite clear whether this was, summing the whole thing or whether it was adding c afterwards. So it's just a little easier to write it in the front so that it's very clear that that plus c is not inside the summation. So another way that we can write this is that essentially the derivative of an infinite sum is just the infinite sum of the derivatives. And similarly, the integral of the infinite sum is just the infinite sum of the integrals. So this is essentially the sum and difference rule, right, which we had for finite sums when we did Calculus 1. And the same holds with infinite sums, which of course are these power series. Looking at the radius of convergence, when we differentiate or integrate, the radius of convergence will end up being the same. So if we take a power series representation for a function, we take the derivative or we take the integral, the radius of convergence is going to be the same for both the derivative and the antiderivative of f. But we still have to check the endpoints because sometimes we can now maybe include some of the endpoints after we integrate or differentiate. And you'll see some examples of that coming right up. So let's take a look here at example 3. So c of x equals the sum from 0 to infinity of, this is an alternating power series, negative 1 to the n, x to the 2n, divided by quantity 2n factorial. Let's use term-by-term differentiation and integration to find power series representation for the derivative and the antiderivative, and then find the corresponding intervals of convergence. So let's go ahead and start off with the derivative. And I'm going to do this in both the expanded form and the closed form. It's not 100% necessary to write out the expanded form, but I do think it is really helpful for us to kind of see how things might change as we take derivatives or take integrals. So let's do c of x. Oh, I'd like to switch back over to blue here. C of x equals. Now I'm going to actually write out the expanded form of this first because I feel like that's easier to do the derivative, and then we'll kind of see how that affects this closed form. So imagining the expanded form, if n equals 0, I'd have negative 1 to the 0, which is just 1, x to the 0, which is 1, 0 factorial. I don't know if I'm not sure if we've talked about that. We probably have. 0 factorial is 1 by definition, and then we also have 0 to the 0 is 1 by definition when we talk about power series. So that would just be 1 is the first term then. And then the next term, plugging in 1 for n, notice it'd be a minus, and then we'd have x squared, because n is 1, so x squared divided by n is 1, so 2 factorial. The next one, n equals 2, would be plus, because this would now be a negative 1 squared, x to the 4th divided by 4 factorial. So hopefully you see where this is going. I'm going to do another one. The next one would be a minus, x to the 6th over 6 factorial, plus, and I think we're feeling okay with doing the dot dot dots from here. I tend to like to do plus dot dot dots as opposed to minus dot dot dots, so I'll usually go out as many as I need to get a plus dot dot dot. It doesn't matter though, if you write minus dot dot dot, that's fine. And this in its closed form is 0 to infinity of what we have up here. Okay, and I'm going to try to leave myself some space here to do the integral as well. Probably should have written a little bit smaller, but that's okay. Okay, so now we're going to take the derivative. Actually, you know what? I can probably just go ahead and do it over here. So we're going to take the derivative. The derivative, term by term, the derivative of 1 is 0, minus, this would be 2x over 2 factorial. Now it would be plus, now remember that I'm taking the derivative with respect to x here. So this would be 4x cubed over 4 factorial, minus 6x to the 5th over 6 factorial, plus dot dot dot. And then we're going to try to write this in the closed form as well. I think before we do that, we probably would want to simplify this derivative a little bit more. So notice what we have is like 2 divided by 2 factorial, 4 divided by 4 factorial, 6 divided by 6 factorial, etc. Let's just look at 6 divided by 6 factorial, for example. So recall that 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. And notice it's going to cancel with that 6, and we'll get is just 1 over 5 factorial. So that means that this can be written as negative x, because it'd be negative x over 1 factorial, which is just 1, plus x cubed over 3 factorial, minus x to the 5th over 5 factorial, plus dot dot dot. And now I could go ahead and write this in the closed form a little bit more easily. where we would end up having, so notice I could also take the derivative of this, and that's another way that we can kind of think about this. Negative 1 to the n, remember we're taking the derivative with respect to x, and so negative 1 to the n is a constant. As is, oh, you know what? Here's what I'm going to write. Let me erase this for a second. I have an idea. Bear with me. Okay, so let's take the derivative of this, and then we'll see how it simplifies to get to the next step down here. So again, negative 1 to the n is just a constant. And then what I'm really taking the derivative of is this x to the 2n part. So I bring the exponent down, and then subtract 1. Right? So it'd be 2n x to the 2n minus 1. Divided by, and just like negative 1 to the n is a constant, 2n factorial is also a constant. So notice what we end up getting is we end up getting this negative 1 to the n, bring that all the way under there, and then the 2n will cancel out with one of these 2n's and become 2n minus 1 factorial. So it'd be x to the 2n minus 1 over 2n minus 1 factorial. Now I like to make sure that when I plug in 0 for n, that I end up getting what I would expect to get. And notice in this case I don't, because if I plug in 0 for n, I actually get x to the negative 1 and then negative 1 factorial, which is no good, right? We can't factorial a negative number, and then I definitely don't want a 1 over x, right, which would be x to the negative 1. We don't have that over here. So notice that what we need to do is we actually need to adjust the index here. So rather than this starting at 0, I need to have this start at 1 instead, so that I end up getting the x to the 1 divided by 1 factorial, which is actually represented with the first term here. So notice that this theorem, which I didn't point out initially because I felt like we didn't have any context for it yet, notice that when we have the power series representation for the original function f, and then the power series representation for the derivative, notice that the index increases by 1. Now it's starting at 1 instead of starting at 0. And that's essentially just from the power rule, because when we take 1 away from the exponent here, we need this to still start at 0, as opposed to starting at a negative 1. And so we just have to increase that index by 1 so that we end up having this starting at 0 like the original power series did. Okay, so this is the power series representation for the derivative of c, so c prime of x. Let's take a look at the integral. Okay, here we go. So now what we're going to do, we're looking at this piece here. We are going to now do the antiderivative to each piece. So the antiderivative of 1 would be x, but before I do that, I'm going to actually do my constant here first. Notice that capital C is already used as the function name, and so I'm going to use a different plus c. I'm going to go ahead and do maybe like a plus d instead. So d is my arbitrary constant. And then what we're going to do is we're going to take the derivative, or sorry, yeah, the integral of 1, which is x. So we'd have plus x. The integral of x squared over 2 factorial would be, so I'm bringing my minus sign down here, add 1 to the exponent, so it would be 3x cubed divided by 3 times 2 factorial, right? So this, the 2 factorial is just a constant, so that's why it's kind of just, coming along for the ride. The antiderivative of x squared is x cubed divided by 3, using the power rule. Okay, and then the next one would be plus. Now this x to the 4th would be x to the 5th over 5, but still times that 4 factorial, minus, we'll do one more, now this term here, adding 1 to the exponent, x to the 7 over 7 times 6 factorial, dot, dot, dot. Now let's go ahead and write that in terms of our sigma notation as well. I should have had an equal sign there though. Equals. Okay, so we'd have negative 1 to the n. And oh, I should have my d plus first on the outside. D plus the sum. Okay, here we go. So now we're going to take the antiderivative of, not that, the antiderivative of this, right, the original function. So negative 1 to the n is just a constant. So it would be x to the, add 1 to the exponent, divided by that exponent times the 2n factorial, right? Okay, let's go and see where that takes me. I'm going to just give myself a little bit more space here. I think I can shift this up a little. There we go, a little more space. Okay, so what we'd end up having then would be d plus x minus, now we're simplifying the expanded form and then also simplifying the closed form as we go to get a nice condensed power series. And so notice this is pretty cool, 3 times 2 factorial, hey, that would be 3 factorial, wouldn't it? So x cubed divided by 3 factorial plus x to the 5th over 5 times 4 factorial would be 5 factorial, x to the 7th over 7 factorial, dot, dot, dot. This is then equal to d plus the series 0 to infinity of, let me bring that over, negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. Now notice that this derivative and this integral are really similar to each other, aren't they? I've got, this is the derivative, and then this is the integral. And notice that they have the same terms, right? X cubed over 3 factorial, etc. But what's different is that, like in this one, the x cubed over 3 factorial is being added, and here it's being subtracted. So it seems as though the derivative is just the opposite of the integral. Right? They're basically the same, they're just opposite in sign. And, you know, I'm not going to worry about this plus c here, but if you kind of bear with me on that, or d, I guess, in this case. But it seems like the derivative and the integral are basically the same, they're just opposite in signs from each other, which is kind of interesting. Now, it actually is not coincidental or anything that happens. If you recall recently, we discovered graphically that this power series representation is actually the cosine function. So we went through and we did, again, the nth partial sum, and we saw that it appeared to just graph the cosine function. And that is true. This is equal to cosine of x. So if we think about the fact that this function is cosine, that this power series is cosine, and we also looked at the interval of convergence in a previous video, in the power series video, and saw that the interval of convergence was all real numbers, negative infinity to infinity. So if we think about how that extends to the derivative and the integral, what we should end up seeing is that the derivative should be the derivative of cosine, which is negative sine. So we've now established the power series representation for negative sine, and then similarly the antiderivative of cosine should be positive sine, plus some constant, right? Let's actually see if that seems to be the case if we were to graph these particular power series. Let's go ahead and do that right now. So we'll hop over to Desmos, and I'm going to go ahead and get rid of what we have here, and we'll just go ahead and do a new one here. So the function, I'll go ahead and use c of x this time, since that's what we used before, is cosine of x. And now we'll do the power series. So sum from I equals 0. Well, actually, we're going to do, yeah. Let's do a few things. We'll do c, and we'll do the derivative, and then we'll do the antiderivative. So this is going to be the original function c, which was negative 1 to the I, x to the 2i, all divided by 2i factorial. Okay, so again, adjusting the slider, we'll go from 0 to, let's just do 20. That sounds good. So again, notice that what happens is we increase the partial sum for the power series. We nicely get this kind of stitching thing happening of where it's just kind of nicely wrapping itself around that cosine function. And then if we were to increase and go even more, like maybe 40, we keep doing that. Notice it just keeps stitching, and it doesn't seem to have any stopping point with its radius of convergence, unlike the other ones that we were looking at where it seemed to go from just like negative 1 to 1 or negative 2 to 2. Okay? Okay, cool. So that is the c of x function. Now let's take a look at the derivative, c prime of x. And I'm going to go ahead and hide c of x because we don't really need to see that anymore, and we also don't need to see the power series for c of x. So here's the derivative, which we know is going to be the negative sine function. And let me see if I can actually type that, or if it gets mad at me. No, it doesn't like that, so that's fine. We just know that it's negative sine. Okay, so now we're going to put in the power series for the derivative that we came up with. Now remember, this one started at 1 as opposed to starting at 0, and then it was negative 1 to the I, x to the 2i minus 1, so I need to do x1 or parentheses there, divided by 2i minus 1 factorial. Okay, so there's the derivative. I'm going to actually change the color on this. Let's maybe make it blue. And then notice as we increase n, we get the same kind of thing happening, where it seems to be nicely wrapping itself around that negative sine function. So it seems like negative sine of x is the derivative. You can also just type that in if you want to, negative sine of x, to confirm that it is in fact negative sine of x, which is the same as the derivative c prime of x. Okay, and then similarly I'm going to hide those. Now let's take a look at the antiderivative, which would be positive sine of x, and then the power series representation that we came up with for that one. That one we were able to keep it at 0, and I'm not going to do the plus d part. You'll kind of see what we can end up doing instead. So we'd have, let's see, negative 1 to the I, and then it was x to the 2i plus 1 divided by 2i plus 1 factorial. Okay, and I already have my slider up pretty high, but you can see how it nicely is kind of wrapping itself around there. Now the plus d part, what we can actually do, well, we can't really find what d is, right, because we don't really have like an initial condition. And notice that when we take the antiderivative, we get this d plus sign. So it's not like we can really like figure out what d is. But in this case, if we kind of just let d be 0 on both sides, we can still kind of get a representation for the sine function as a power series. So to kind of answer my question here, yes. Do the graphs of the derivative and the antiderivative follow suit? Yes, we kind of see the derivative as being negative sine and the antiderivative as being positive sine. Okay, so let's look at another example of how we can use integration to find a power series representation for a different function. We're going to actually find the power series representation for arctangent of x by integrating the power series representation for 1 over 1 plus x squared, which we found in example 1. So recall that the power series representation for 1 over 1 plus x squared, well, we replaced all of the x's with a negative x squared, right? So it was 1 minus x squared plus x to the 4th minus x to the 6th plus dot dot dot, which was the power series n equals 0 to infinity of negative 1 to the n x to the 2n. And I'm just going to double check real quick that that is what we came up with in example 1. Yep, okay. Just wanted to make sure before we kept going, right? Okay, so here's what we're going to do. We're going to find a power series representation for arctangent by integrating this whole thing. So we're going to integrate 1 over 1 plus x squared. Again, anytime we take the derivative or the integral, we're doing that with respect to x, because all of these power series are functions of x. So now we're going to integrate 1 minus x squared plus x to the 4th, x to the 6th, dot, 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 with respect to x, which means what we're really doing is integrating this power series. With respect to x. Okay, here we go. Let's do it. So this is the left side. This is what we're looking for. This is arctangent plus some constant. I'm going to go ahead and use capital C for that. So here I'm going to bring my capital C in for my, and anytime I integrate, right, and with an indefinite integral, we need our plus C. Antiderivative of 1 would be plus x minus x cubed over 3 plus x to the 5th, oops, x to the 5th over 5 minus x to the 7th over 7 plus dot 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 equals, again, my arbitrary constant, plus, now I'm going to look at just integrating this piece here. So anytime I integrate a series, the result is still a series, right? I'm integrating essentially each piece of the series and going kind of piece by piece. So again, this -1 to the n is just a constant. Now what we did is we did the antiderivative of x to the 2n. When we do that, we add 1 to the exponent and then divide by that exponent. Okay, which notice does match the pattern that we see here. 2n plus 1 would be odd numbers. And notice when n is 0, we would have x to the 1st divided by 1. And then when n is 1, we'd have x cubed divided by 3. Right, and then the positives and negatives are also following suit. Okay, so that means that we can have a power series representation for arctangent, because essentially what we can do is we can basically subtract c from all of the sides here and solve for arctangent of x, because that's what we were trying to do, is we were trying to get a power series representation for arctangent, not necessarily arctangent of x plus c. So arctangent is x minus, well actually I can just go ahead and I'll just write the closed form. So here's the power series representation for arctangent. -1 to the n, x to the 2n plus 1 divided by 2n plus 1. Pretty cool. So now we've represented lots of things as power series. Rational functions, 1 over 1 minus x, 1 over 2 minus x, 1 over 1 plus x squared. We've looked at representing trig functions, sine, cosine, and now we have an inverse trig function, arctangent. Now the interval of convergence, let's go ahead and check that. Now we know that the radius of convergence is going to be the same, because when you integrate or differentiate, the radius of convergence stays consistent. But sometimes we can include endpoints as well. Let's go ahead and see. So we know that it's going to be absolute value of x has to be less than 1, but we need to check x equals -1 and x equals 1. We need to check the endpoints. Let's go ahead and start with x equals -1. Okay, so then we would end up having, now first thing, I know I can take the arctangent of -1, so the left side is seeming okay there. The right side, looking at the power series, if x equals -1, I would end up having -1 to the 2n plus 1 for 2n plus 1. Let's see what that comes out to. So -1 to the 2n plus 1, 2n plus 1 is always going to be odd, which means that -1 to that power is always going to be -1. So if we imagine -1 to the n times a -1, that is just -1 to the n plus 1, divided by 2n plus 1. So n plus 1 is going to alternate between it's going to alternate between evens and odds depending on what n is. So that means that -1 to the n plus 1 is going to alternate between positives and negatives. So this is an alternating series. So we can use the alternating series test, and we need to check 3 things, right? First off is 1 over 2n plus 1 is positive. Yes, it is, for n being positive. Is it decreasing? Yes, it is, because as n increases, 1 over 2n plus 1 will decrease. And then does its limit equal 0? Yes, it does. So by the alternating series test, this series converges. So that means that I can actually include the endpoint of -1, unlike all the other ones that we've been looking at where we couldn't include that. Let's take a look at x equals +1. That would give me the series. Let's see, this would end up being 1 to the 2n plus 1, which is just going to be 1. And I'll end up having -1 to the n over 2n plus 1. Notice this is the same. This is still an alternating series. It just now starts at a positive number instead of starting at a negative number. But that doesn't affect the convergence. This still converges by the alternating series test. And so we can also include the other endpoint. So that means that the interval of convergence, I've been kind of using pink for that, so maybe I'll stick with that. Come on, pink, work with me. interval of convergence would then be -1 to 1, but including the endpoints. So that's why we have those brackets instead of parentheses. Okay, here's an opportunity for you to try one. Find a power series representation for the natural log of 1 plus x. Now, the instructions here are, somewhat limited. So if you want a challenge, go ahead and pause it right now and give it a try. If you want a little hint, then keep listening. Okay, again, if you want a challenge, pause and just try it on your own. Okay, here's a little hint if you need one. Consider the fact that we can make the power series representation for 1 over 1 plus x relatively easily, and then we can use the integral to create natural log of 1 plus x. Okay, so if you haven't paused it already, go ahead and pause and give it a try now that you have that hint. All right, welcome back. Let's go ahead and see how that one went. So we've got, so first thing we're going to have to do is start by creating the 1 over 1 plus x function power series from the 1 over 1 minus x power series. We haven't done that yet. But it's pretty straightforward because we're just going to think of this as being 1 over 1 minus negative x. So that means that we're going to replace all of the x's in that original power series, 1 plus x squared, etc., with a negative x. So it would be 1 plus negative x plus negative x squared plus negative x cubed, dot, dot, dot. And then our power series form for that would be negative x to the n. Okay, and then this is now 1 over 1 plus x. I get 1 minus x plus x squared, right, because negative x squared would be positive x squared, minus x cubed, so we get this alternating series. And then this would be -1 to the n, x to the n. Okay, so basically now we just have this alternating power series. Okay, next thing we're going to do is we're going to find the power series representation for natural log of 1 plus x by integrating both sides. I guess all three sides, huh? With respect to x, of course. Here we go. So we know that the antiderivative of 1 over 1 plus x is going to be the natural log of, now I'm going to do the absolute value in this case because we really do need that. When we take the antiderivative of 1 over x, we get the natural log of the absolute value of that thing. So it'd be the natural log of the absolute value of 1 plus x plus some constant, right, is going to be a constant, plus the antiderivative of x, which is, or sorry, antiderivative of 1, which is x, minus x squared over 2, plus x cubed over 3, minus x to the 4th over 4, so we're just integrating term by term, equals the constant, plus, now it's going to be the series, -1 to the n is just a constant in terms of the integral, because I'm integrating with respect to x, and then there'd be x to the n plus 1 divided by n plus 1. You could extend that fraction bar if you wanted to. There we go. Now if you just get rid of the c's on all the sides, then what we'd end up having is natural log of absolute value 1 plus x. You might be worried about the absolute values, but I'll get to that in just a second. And then actually let's just go ahead and write it in the closed form. So it'd be -1 to the n, x to the n plus 1 divided by n plus 1. So now when we are looking at the interval of convergence, we can probably get rid of this absolute value sign because there's only going to be certain x values for which this particular one stands. So checking the endpoints, we again end up seeing that we're going to be kind of starting with this, and so then we're going to check to see if we can do the endpoints or not. Let's look at x equals -1, for example. The first thing I'm going to notice here is that if x is -1, what I'm going to get is the natural log of 0. Now I know that the natural log of 0 is undefined because we cannot take e to a power and get 0 as a result. So -1 is not going to be able to be included in this case. We can also double check it here to kind of see why that would be the case. So if I do -1, what I'd end up having is -1 to the n, and then this would be -1 to the n plus 1 over n plus 1. And now notice that what happens here is that I'd have -1 to the n and times a -1 to the n plus 1. These are always going to be alternating, or I should say these are always going to be opposite in sign. That is, if n was 2, then I'd have a -1 squared times a -1 cubed, right? Which would end up being a -1 in the end. This is always going to be -1. Another way you can see this is it would be a -1 to the n times n, we would add them together. N plus 1, which would be 2n plus 1. 2n plus 1 is always going to be odd, which means that -1 to that is always going to be -1. So this is not an alternating series. It is always, this is equal to -1 over n plus 1. Now notice this is very similar to the harmonic series. I could do a limit comparison test on this. I feel pretty confident in saying that this is divergent, just because, well, maybe because I'm feeling a little bit lazy. Divergent by the limit comparison test. You could go through that limit, you'd end up getting 1. Feel free to do that. But we can see this is very similar to the harmonic series. It's going to end up diverging. Again, it's not an alternating series. It's always, the terms are always going to be negative. So divergent, so I can't include -1, but let's check +1. So if x equals 1, then I would end up having the series -1 to the n. Now 1 to the n plus 1 is always just going to be 1 over n plus 1. This one is going to converge by the alternating series test because we have that the 1 over n plus 1 is positive. It is decreasing. And the limit as n goes to infinity of 1 over n plus 1 equals 0. Check. So converges by the alternating series test, which means that our interval of convergence is -1, not included, to +1, which is included. Whew. Now I want to point out something interesting. Notice that when we let x equal 1 on this side, we got a convergent series. What we ended up getting is the series -1 to the n over n plus 1. And that equals the natural log of, now I can also let x be 1 over here, which would give me the natural log of 2. So what we've actually shown is that this particular series, this particular alternating series, converges to the natural log of 2, which is quite interesting. Another thing to point out here is that because of the fact that this particular domain is set on this power series, then I can get rid of the absolute value because I can see that on this interval we would not be having any negative numbers in here. So I could go ahead and actually get rid of these absolute values and go ahead and put in my parentheses, because I'm not stating that this is equal for all x. This is equal only for x on this interval. And let me point out also that another way that we could write this particular series here is if we shift the index to now start at 1, notice that we have this starting at the 0 power, so this would be -1 to the n minus 1 in order for it to start at the 0 power. And then this starts at 1, doesn't it, when n is 0. So if I start at n equals 1, this would be n. So really what we have is that the alternating harmonic series converges, which we already knew, converges to the natural log of 2. Pretty cool. And you saw in the video where we looked at some of the partial sums of the harmonic series, the alternating harmonic series, that it seemed to be converging to about 0.69 something, and 0.69 is the decimal approximation for the natural log of 2. Okay, last example, we're almost there. You're doing a great job of keeping up with me here. So let's look at another application to power series. Evaluate the indefinite integral 1 over 1 plus x to the 4th as a power series and find its interval of convergence. And then we're going to use that to approximate the definite integral from 0 to 0.5, accurate to 6 decimal places. Okay, here we go. Let's go ahead and start off with evaluating this indefinite integral. Now, first thing I want to point out is this indefinite integral would be very difficult to find just in general. Like, we couldn't use a substitution here. If there was an x cubed up here, right, then I could use an easy substitution and I probably wouldn't even bother with power series. But 1 over 1 plus x to the 4th is a rather complicated integral to find. You can also see like integration by parts wouldn't work. If you actually go to like Wolfram Alpha or something and look at the antiderivative, it's rather complicated. Actually, here, I'll show you, just to give you some incentive as to why we might want to use power series to represent this. So let's just go to Wolfram Alpha. And if I type in integral 1 over 1 plus x to the 4th, here's the antiderivative. Yikes. Anywhere that it uses log, it's actually is referring to the natural log function. I'm not sure why they write it as log, but as you can see, it's quite daunting and I would not want to try to go about finding it. So instead, what we're going to do is we're going to try to represent this indefinite integral as a power series because it's very easy for us to find the antiderivative of polynomials, which is, again, essentially what a power series is. Okay, so let's do that. Sorry, jumped up there. Okay, so first thing we need to do is actually create 1 over 1 plus x to the 4th. And I think we've gotten pretty good at doing that, haven't we? 1 over 1 plus x to the 4th. Essentially what we're going to do is we're just going to look at 1 over 1 minus x. We'll go ahead and do that here. We're going to look at that original power series. Okay, and then what we're going to do is we're going to replace x with, in this case, a negative x to the 4th, so that we end up getting 1 over 1 plus x to the 4th. Okay, I think we're probably past the need for additional colors here, so I'm going to go ahead and just roll with it. X to the 4th squared, negative x to the 4th cubed, dot, dot, dot. Then this would be a negative x to the 4th to the n. Okay, so that means that 1 over 1 plus x to the 4th is going to be 1 minus x to the 4th plus, because I'm squaring the negative, this would be a positive x to the 8th. Now I'm cubing the negative, so this would be a minus x to the 12th plus dot, dot, dot. And so we end up getting this alternating series, and that of course comes from the negative to the n part, x to the 4n, multiplying those exponents together. So that's the power series representation for 1 over 1 plus x to the 4th. Now what we want to do is try to represent this indefinite integral as a power series. So we are going to integrate both sides, or I guess all 3 sides. So what we'd end up getting, I'm going to actually go ahead and leave out the plus c's this time for a few different reasons. One, I can always subtract c from all the sides, right, and end up getting the thing that I'm looking for. Also, we're going to eventually use this to look at a definite integral, and then the plus c's really don't matter in that sense. So I'd have x minus x to the 5th over 5 plus x to the 9 over 9 minus x to the 13 over 13, etc. And I still have an alternating series, and now I've added 1 to the exponents and divided by that same exponent. Okay, here we go. So this now is the answer to the first part. I have now represented the indefinite integral 1 over 1 plus x to the 4th as a power series. So now what we're going to do is use this to approximate the definite integral. So now I'm going to look at the definite integral from 0 to 0.5. I'm going to look at approximating this definite integral accurate to 6 decimal places. So that means since this is the antiderivative, I'm essentially taking this thing and evaluating, oh, I need my plus dot dot dot, evaluating it from 0 to 0.5. Similarly, I am taking this power series and evaluating it from 0 to 0.5. Okay, so now what we'd end up having is I can plug in the bounds. So notice that plugging in 0.5 would end up giving me 0.5 minus 0.5 to the 5th plus 0.5 to the 9th minus 0.5 to the 13th, oh, divided by, oh, I lost some things, didn't I? 5 divided by 9. You're probably like, wait, Austina, slow down, you missed that. 0.5 to the 13th over 13 plus dot dot dot. Now notice that when I plug in 0, I'm going to end up getting minus 0. So I'm going to not even bother doing that or writing that. And then what I end up getting over here is now no longer a power series, right? Because now I'm actually plugging in a number for x. Now I just actually have a series, 0.5 to the 4n plus 1 over 4n plus 1. Okay, so what we have is essentially this infinite series. We know that this series converges because the radius, or the interval of convergence, is, right, we started with this, we replaced all of the x's with a negative x to the 4th. Whoops, I'll do that. There we go. So now we have this, and then this means x to the 4th is less than 1, which is still meaning that the absolute value of x is less than 1. We could go through and check the endpoints, but I can kind of see that a negative 1 to the 4n, now I want to look at this one, negative 1 to the 4n plus 1, that would always be a negative number. Well, in this case, actually, I'm not going to check the endpoints because we don't really need to here. All I'm interested in is, can we plug in 0 and can we plug in 0.5? And the answer is yes, we can, because both 0 and 0.5 are in this particular interval. Okay. I'll put a little side note here that we didn't check the endpoints. Okay, so we know that we can do this. We can plug in 0.5. So what we have then is this infinite series that represents the value of the area under this curve from 0 to 0.5. So the question is, we want to try to approximate this accurate to 6 decimal places. Now notice that this is an alternating series, which means that I can use the alternating series estimation theorem. Let me write that out for a second. Now recall that the alternating series estimation theorem states that that essentially the sum is going to be, the partial sum is going to be as good as the next term. And that's because we're adding and then subtracting and then adding and then subtracting, etc. And so that means that the remainder is always going to kind of have this bound on whatever the next term is. So what I can do is I can actually just look at these individual terms and see which one is smaller than up to 6 decimal places. So if we're looking for an accuracy of up to 6 decimal places, and that would be 0.0000001. Now I know that I've written, I've written 6 zeros here. If I just went out to 1 here, then this would be accurate to 5 decimal places. I need an extra 0 there. There we go. Okay, so looking at, I'm going to need to use Desmos for this to help us do some number crunching. Okay, so if I look at 0.5, clearly 0.5 is not going to be good enough. But if I look at the next term, 0.5 to the 5th divided by 5, what I have is 0.00625. And so that's not, I'm looking for it to be smaller than that 0.6 zeros and then a 1. So now we'll do 0.5 to the 9th divided by 9. Nope, not quite. I think we need to go another one. 0.5 to the, I think this one's going to do it, to the 13th divided by 13. Oh, still not quite the accuracy that we're looking for. So we're going to have to go one more to the, let's see, the next one would be I'm adding 4 each time. So to the 17th power divided by 17. And there we go. Notice that we have it up to 10 to the negative 7th power. But you know what? This would actually be 0.6 zeros and then a 4, which is actually bigger than having a 1 here. So I think we actually need to go one more. 0.5 to the 21st divided by 21. That definitely does it. Now we have 10 to the negative 8th power. Okay, so we have to go, how many terms then? So we need to add, so I'm going to do an approximate sign here now. We are going to pull Desmos back up in just a second to do our number crunching. So we're going to say this is approximately 0.5 minus 0.5 to the 5th over 5 plus 0.5 to the 9th over 9. And we went to the 21st, didn't we? Okay, so it's going to be approximate. This is going to be accurate to the 6 decimal places that we're looking for, which notice that this is equivalent to the partial sum starting at 0 and going to, let's see, what n value would make that 21, n equals 5. So we're going to go up to the fifth partial sum. Here we go. I'm going to actually type this into Desmos as opposed to typing out all of these plus, minus, etc. Okay, so here we go. We're going to do the sum. And now you can keep it as an n here because we're doing a finite partial sum here. Well, I guess all the partial sums are finite, but we're not putting n as the upper bound. So negative 1 to the n, 0.5 to the 4n plus 1. Divided by 4n plus 1. What doesn't it like? 4n plus 1. Oh, you know what? I think, it doesn't like that because I used some slider stuff. So here's what I'm going to do. I'm going to copy this, and then you could also change the index to something else, but I'm going to copy it and just refresh my screen here. And that way I don't have to retype it in, but now Desmos doesn't have to worry about what that n value thing is. Okay, so this is approximately 0.493958. I'm going to keep going. 0.49946. Now to check to see if this is in fact accurate to 6 decimal places, what I can do is actually look at what is the value of this definite integral, and I can do that in Desmos. Just like you can type SUM to create a sum, you can type in INT to create a integral. 0 to 0.5, 1 over 1 plus x to the 4th dx. And notice that what I end up getting is a pretty good amount of accuracy if you look here. I'm going to go ahead and call this S for sum. I'm going to call this I for integral. And that way I can come down here and just subtract the 2 and see the level of error that I have. And notice that that error is pretty darn good. I get a 10 to the negative 9th power. Whereas if I had only gone to 4, and actually notice it is actually still accurate even up to using the 4th partial sum. Let's see, maybe if the 3rd would have worked. 3rd would not have worked because again this would now be 0.0 and be, notice that it's good up until 1, 2, 3, 4, 5, but not the 6th decimal place. One has a 7, one has an 8. But now if I go to 4, I've got it accurate up to the 6th and actually even the 7th decimal place as well. So technically I only need to go up to the 4th partial sum, but the alternating series estimation theorem, again, is just kind of like your what's going to be sufficient. The 5th one is definitely going to be sufficient in this case. It turns out that the 4th is also sufficient. Okay, well I hope you enjoyed seeing some extra applications to these power series, and it's going to keep going. We're going to look into some things called Taylor series and Taylor polynomials and continue to see these really cool applications to power series.